That's the housekeeping done for the day. I'd like to start by welcoming and introducing to you Charles Wood, who sat with me here in the WTIN studio. Very welcome, Charles. Charles, for those of you who don't know him, is the Managing Director of Boltex, the UK-based specialists in warp-knitted technical textiles. And most relevant, actually, to today is the Chairman of the Textile Institute Special Interest Group. Charles, would you like to say a few words?
Yes. So first of all, Mark, huge thanks to you and the rest of the team at the WTIN for giving us a wonderful, warm welcome today. So here we are in Leeds at their headquarters. We're very pleased to host this event today. Big thank you to all of our panelists for their time and commitment for the event today, which should be really interesting. Focus on obviously such a key and topical area of material science. I'd also like to thank all of you for joining. The Technical Textile SIG, Textile Institute, has rekindled it this year, and we're looking to promote various things from educational, but also networking as well, to join different elements of industry, academia, the different sort of elements of the Textile Institute together. So huge thanks to everyone. Thank you all for joining, and looking forward to a great event. Thank you, Mark.
Thank you, Charles. So what we thought we'd do, just to get things started for you, we have a fantastic panel of specialists with us today, but you may not know all of them. So we thought it might be a good way to get things started by asking each of the panelists to perhaps introduce themselves, tell us a little bit about themselves, and also give us their view as to where we're at today with graphene and 2D materials. So to kick things off, Dr. Nasmul Karim, the Associate Professor at the Centre for Print Research at the University of the West of England in Bristol, here in the UK. Nasmul, very welcome. Perhaps you can tell us a little bit about yourself.
Thank you so much, Mark. Good morning, good afternoon, and good evening, depending on where you are in the world. My name is Nasmul Karim. I'm a textile engineer by training. I currently work at
We're going to reshuffle.
Work at UWE, which is University of West of England in Bristol, as an associate professor there. I lead a research team called New Material Towards Sustainable Technologies. So my team is currently looking into graphene and other 2D material-based technology, mainly for wearable electronics, for personalized healthcare applications, high-performance functional clothing, and fiber-reinforced composites as well. Previously, I was at National Graphene Institute of University of Manchester, where I led graphene textiles research activities. So my journey for graphene and other 2D materials started in, well, I was a PhD student at University of Manchester from 2012 to 2015. During my PhD, we developed first all inkjet printed graphene e-textiles. Then in 2015, when National Graphene Institute was opened, so I joined the team, and then we made a number of breakthroughs in graphene textiles areas. We developed highly scalable way of producing graphene fabrics and yarn, and then we also developed graphene fabric, which is highly conductive by using existing textile coating and printing technique. So I assume you all know a little bit about graphene, you have heard about all the incredible properties of graphene: stronger than steel, stiffer than diamond, thinner than human hair. So which are all good in an atomic level. But for textile application, what we really care about is the first of all is the multifunctional aspect of graphene. So graphene not only provides the electrical and thermal conductivity, but also it provides it improves the mechanical properties of the fabric. And the second thing is the low temperature processing. So whatever technique we have done, we have been researching on, we used very low temperature process, which is really opened up, which has given us the flexibility to use various kind of material of the fabrics. So in the past decade, we have seen huge technological development in graphene area. There has been a lot of interest in graphene fabrics. So in 2018, I was very fortunate to receive some funding from Innovate UK to basically to travel around the world and speak to at least 100 companies just to understand and validate our graphene textile research activities. So I traveled far east to far west, spoke to companies across the value chain, from textile manufacturer to quality controller, retailer, R&D. So what we found from that study was there are two potential application of graphene textiles, which, so number one is the high performance functional clothing, so which would be more short or near term applications. And then the wearable electronic textiles, which is more kind of like a future application of graphene textiles. And in terms of the challenge, so what I see is there are kind of like three challenges we probably need to address to be able to successfully commercialize graphene textiles. Number one, we need to have 2D material which can be produced in a scalable quantity at cost. And secondly, as you know, the textile is very traditional process, traditional industry. Maybe people are very reluctant to change the existing manufacturing process or technique. So, it is quite important that we use very simple and scalable way of manufacturing graphene textiles. So if we want to win something very big, we need to use existing textile process and manufacturing. Finally, the product we make need to be safe to use and extremely durable and washable. So this is what exactly we have been addressing in our lab, in our day-to-day research activities. So that's all from me for now. Thank you.
Thank you very much, Nasmul. You've been very busy, clearly, on this particular subject, and we look forward to learning more from you in the coming hour or so. So next up, I'd like to invite Dave Vanek, Director of Sales and Business Development at Graphene One, who is joining us today all the way from Charlotte in beautiful North Carolina. Dave, good morning to you.
Thank you. Yeah, I'm going to say good morning since it's not even 8 o'clock yet here in Charlotte, but it looks to be a beautiful day. So you're already ahead of me. But yeah, thank you for inviting me. I love to get a chance to talk about what we're doing. I'm a chemical engineer by training, and I'm still learning textiles. I've been with Graphene One now a little over 2 years. So I'm learning textiles, and I have to rely on experts like you on figuring out how to make the best fabrics from our materials. But our company, Graphene One, is part of a larger parent company, a 30-year-old private company based in China, outside Shanghai, that's made safety gloves for cut-resistant handling of materials for over 30 years. That's their base. Business was knitting safety gloves. They started their own division for safety gloves, their own brand of safety gloves about 10 years ago called Armor Guys. And they first put the graphene fiber in the ultra high molecular weight polyethylene fiber and looked at it in gloves. And actually in their gloves, it enhanced the cut and abrasion resistance of the gloves. And it brought other functional properties I'll talk about in a minute as well. So they started looking at what could you do with it. They make their own graphene, and they make graphene oxide from that. And then they put the graphene oxide into a concentrate and put that into standard textile polymers, polyester, nylon, and viscose. So we have staple and filament form of those three. And so they look like traditional fibers that are used every day in our textiles that we're wearing. And my job is to work with brands and with mills to figure out how to use those. And the key benefits that we're promoting, if you will, are antibacterial, anti-odor, and thermal regulation. So we typically tell people to, if you have 30 to 50% of our fiber, and our brand is Karim. So if you have 30 to 50% of the Karim fiber in your fabric, so cotton with Karim polyester, so cotton polyester t-shirt, something like that, then you should get these properties that we're talking about, and you can design those to bring those features to your clothing. The graphene oxide is a particle. It is not, connected. It's not continuous, so we don't get electrical properties. I know the other speakers are going to talk about smart fabrics and the future. We don't get electrical conductivity. I get people wanting to do that, but I'm like, we're not promoting that. We're not there yet. We're working on functional characteristics. So keeping you warm or cooling you, so thermal regulation, spreading the heat, dissipation, if you will, or the antibacterial. So we have commercial applications. We've been selling in all over the world. The fibers made outside of China. I handle the US, Europe, and about all the other regions, but it's now being used in socks, underwear, denim, jackets, bedding, textiles, sportswear, so a wide variety of clothing, and it's been commercial for 3 or 4 years, and it's starting to take off now with some major brands. So and I look at the future. I think the future is very bright for graphene. The research going on at universities and companies around the world is incredible, and it spans from concrete and plastic materials, composites, semiconductors, batteries. So there's a tremendous amount of effort going on. The challenges will be to have the graphene in the right form for the right application and be able to implement it in the existing technology. And that's already was mentioned by Nasmul, that you have to have it. If you want to get it into textiles, it has to be able to be woven and knit on existing equipment and be able to be dyed. And that's the good part of our Karim fiber. We're putting in a small amount, and it really does not affect the normal knitting, dyeing, handling of the fabric. So any mill can really use it. If they are doing a polyester today, you put the Karim polyester in there. You can swap out whatever you use for the Karim, and the normal process of making the fabric is the same. So the real challenge in our application is putting it in a fabric in a smart way, so that it actually brings the benefit to the end garment that they were initially looking for. And I'll leave it with that for now.
Dave, thank you, and great to hear about some real world examples of how graphene is currently being utilized. So moving on, next I'd like to invite Dr. Shayan Sayedin, I hope I've said that correctly, Assistant Professor in Digital Materials Manufacturing at the University of Newcastle, which of course is in Newcastle, here in the UK. Shayan, good afternoon to you.
All right, thank you very much, Mark. So my name is Shayan, and I'm a lecturer or assistant professor in digital materials manufacturing in Newcastle University. So my research predominantly focuses on discovery of new 2D materials beyond graphene and processing those materials in various wearable applications. Wearable sensing platforms and wearable energy storage. And my passion is essentially incorporating these 2D materials within individual fibers, and then taking those and making fibers, making textiles, making yarn out of these materials. So my journey is a bit all over the place, really. So I am a chemical engineer by training, but my focus of research during my master's was on fibers and textiles. I started with doing a little bit of electrospinning, which is essentially using electric current in order to make fibers. And then I became very interested and passionate about conducting polymers. So at the time, I was very excited to see that plastics like polymers can conduct electricity, and that took me to Australia to the Intelligent Polymer Research Institute in University of Wollongong, and I was interested to essentially make these conducting polymers into fibers and textiles for wearable applications. And in 2012, there was a lot of buzz around graphene, and we had a Nobel Prize in discovery of graphene in 2010. So I became interested in using graphene, and then I started by a technique called liquid phase exfoliation in order to produce solutions like these, which is essentially graphene in a solvent. Like it could be water, it could be like organic solvents. And we've heard a lot about graphene being very thin, so I can add to that and provide some more quantitative measures, being in terms of dimension 100,000 times thinner than human hair, or 10,000 times thinner than cling wraps that we use in the kitchen. So you can't really see these things with the naked eye, but they can be present, they can be processed in solution, for example, and that's the advantage that we could utilize in fiber-based applications. We could print it on top of textiles, we could incorporate it into conventional yarns, we can make functional yarns as discussed, and these functional yarns could be used for a variety of applications, okay? And that was essentially the first thing that I did. But during my PhD, I came up with an approach of producing a new type of graphene solutions, which is essentially, which contains very large sheets, and that forms liquid crystals. So this is essentially called liquid crystal graphene oxide. So it's a similar type of solution, but it's got a lot of functional groups on the surface that enables its processability. And having large sheets and liquid crystal domains enables a lot of functionality, such as reinforcement that was talked about. So as you can imagine, graphene application is not only in making conductive fibers, it can also be used for reinforcing, making a stronger fibers, making, durable fibers, and making tougher fibers. So just to give you an idea, 0.3% of this material in a fiber resulted in a conductive fiber, and that led to 10 times enhancement of stiffness, which is very important for a variety of applications. So during my PhD journey, I made fibers that are very elastic and also conductive, and having essentially two different properties of being elastic and conductive, then that enabled me to make sensor fibers, fibers that can sense movement. Essentially, these fibers change resistance when they are stretched. And that could be used for making wearable devices or textile-based wearable devices that can monitor body movement. So this is some of the yarns or fibers that I produced during my PhD. And these are essentially made by incorporating graphene inside polyurethane fibers. So as opposed to coating the fiber with graphene or with other materials, I just incorporated graphene inside these fibers and made individual fibers. And then I took it to the next step. I made textiles out of these. So made it in the form of a textile patch. That could be, so the black stuff that you see in the middle is just essentially these graphene fibers that were made into a textile fabric. And the beauty of this piece of fabric is it essentially changes its resistance. And by changing this resistance, you can monitor your body movement, for example. And my journey on using graphene and 2D materials didn't stop there. So in 2015, I received a fellowship at Deakin University in Australia, and that enabled me to essentially explore my ideas. At the time, I had this crazy idea that could we make yarns and textiles that can store energy, essentially variable batteries. But they're not exactly batteries. There are other type of devices called supercapacitors. So they are essentially devices between capacitors and batteries. And they are made by using two of these graphene fibers or yarns and then covering that with a layer of electrolytes. And using that simple structure, we could make fibers that can store energy. So similar to the way that a battery does. And you know, that was essentially the work that I've done during my PhD, but and postdoctoral research in Australia. But I moved to the US as well, worked for about a year at Textile University in Philadelphia. And there I started working with a new type of 2D material called Maxine, which is essentially titanium carbide. Maxine has much higher conductivity than graphene. So arguably, the conductivity of Maxine is 100 times higher than a typical graphene produced using liquid phase exfoliation. But it's not only about conductivity, it's also about other properties that we can utilize. So, for example, energy storage and things like that. And I use Maxine in order to make textiles that can sense pressure. So essentially 2 pieces of titanium carbide coated textile with a layer of dielectric material that could essentially be used for pressure sensing application. And after a bit of work in the US, I moved to Imperial College London, worked in Imperial College, worked with a wide range of 2D materials, things such as MOS2, which is this guy. It's similar again in the form of a solution. And there I worked in solar cell based devices and transistor based devices. And essentially after completing my journey at Imperial College, I moved to Newcastle University and I started working here. And this is essentially my journey. I'm very passionate about 2D materials beyond graphene and how we can harness and utilize their full properties in fiber-based application, not only conductivity, but also reinforcement, energy storage, sensing, and beyond.
Cheyenne, thank you very much. It's great to see your energy and your enthusiasm for this topic. It shines through. Also great to see some examples. It's always good to actually physically see these things. So thank you for sharing those with us. Finally, I'd like to introduce Emerson Whitworth. Emerson is a sales executive at Haydale, which is in Oldham here in the UK. In fact, not too far from where we're based here in Leeds. Emerson, good afternoon. You're very welcome. Perhaps you can share a little insight into you and your business.
Yeah, so welcome everybody. Thanks for joining. Thanks for the invite, guys. So obviously I've worked in print and packaging for the last 25 plus years, and 23 years of that was in the standard inks that you would see in the supermarket on bags and tins and cans and lids. But for the last 2.5 years, I've worked for Haydale Technologies, and we're developing novel solutions using functional inks. So our core USP is that we choose our materials, whether they be graphene, carbon nanotubes, or other materials. And we put them through a surface functionalization in our patented plasma reactors down in Swansea, where the factory is based. And then we use these, in a customizable process and chemistries to enhance matrix interactions with polymers, water, and solvent-based systems. So my job primarily, as my title portrays, is ink technology. So we've been working quite well now using our printed inks on certain textiles. Because we covalently bond different chemical groups onto the surface of 2D graphenes or carbon nanotubes, we can choose different levels of different chemistries. So whether it be oxygen, amine, fluorine, to give them different end-use properties as the customer wants. So the chemistry itself that we put on is non-destructive, so it doesn't affect the graphene at all. And then we use that, like I say, in intermediates for inks, dispersions, polymers, composites, and coatings. So similar to what Nasmul was on before, obviously that gives the product thermal and mechanical improvements, as well as already having the electrical capabilities that graphene and 2D materials give us. And it's used in, transportation, energy, the electronics sector, packaging, construction. We've had great strides recently in the biomedical world, and obviously into textiles, which we're all here talking about today. So the main properties that we're uplifting is anti-static, especially antibacterial now, and antimicrobial. The 2D format leads itself to give what they call a nano knife, which cuts through the bacterial walls and kills disease. So very, very specialized in certain areas for that. Obviously, lightweighting, the guys have already alluded to as well. But what we've managed to do over the last 2 years already is scale it up into a process that makes it commercially viable already. We have real world solutions that are being used out there already, and this is starting to pay us back. Most recently, we developed some apparel with the British Olympic team that was used in the Tokyo Olympics that led to a certain amount of medals being won in certain sports, and you can read all about that if you research Airedale. You'll see it online. We work with cotton rich and synthetic materials, and our products, once printed, also can be encapsulated to give it a little bit more longer shelf life, but it is very good at washability as well. So we also use it for EMF shielding. Due to it being highly conductive, it also, it reflects and absorbs radiation. So that's another growth area in the textile market currently that we see quite a lot of traction in. We have looked in and we have worked into yarns, similar to what some of the other guys have been talking about regarding melt spinning into polyester and nylon and other synthetics to give a graphene incorporated yarn as a raw material then to go out and print certain apparels. So from our side, obviously, inks wise, we don't just do that. I do other things in biomedical, in pressure sensing, which I'm sure me and Cheyenne could talk for hours about, and a few other crazy areas that are all under NDA. But hey, it's a weird world, and we see a great future for graphene, and we've got some great products.
Emerson, thank you. Thank you very much indeed to all of you, actually. And it strikes me we've really got a great balance here between research on one side and commercialization of these products here and now on the other. So for the benefit of our audience today, we're now going to divide up the discussion into 4 areas. We're going to start in a moment by establishing the fundamentals of graphene and 2D materials. We'll move on and have a discussion around what today's market is looking like, then on to sustainability, and finally onto future developments. And I would remind you all that if you do have a question, please, the chat function, we're all familiar with it now, please put your question into there and I will then share your question with the panel. So, we're well represented in our audience today with a number of students from around the world. And it seemed quite a good opportunity at this stage just to establish exactly what we mean by a 2D material. And I'm going to put that first. I'm going to put it to all of you, but perhaps I'll put it to you first, Nasmul.
Thanks, Mark. I think if I just, very fundamental way define what graphene is a single layer of graphite. So if you consider graphite as a three-dimensional structure, there are thousands layers of graphene loosely connected to each other, and what we do is loosely connected to each other using a van der Waals force. So what we do when we make graphene is try to overcome those forces. So we apply various kind of process like ultrasonications, shear mixing, microfluidization in order to overcome those forces to get to a single layer. And when it gets to a single layer, it becomes graphene, and it shows all those incredible properties. So that's kind of like a basic definition of graphene.
Excellent. Would anyone like to add to that? Are we all in agreement with that? Cheyenne, I think you...
Yeah, I just have a few additional points. So, for example, this is a sticky note, right? So you can imagine this being layers of graphene connected to each other in a graphite structure. So you can essentially peel off one of these layers, right? And that's essentially your single sheet of graphene, okay? So here, essentially, this is the graphite structure. It's not exactly like this. They are not really bonded to each other. They are just sitting there on top of each other in a form of, some van der Waals forces that are binding these sheets to each other. And these van der Waals forces can be easily broken by, application of, mechanical forces like shear. Nasmul mentioned a lot of approaches that are used for breaking these bonds. But just to add that, this, when we talk about graphene, we mean, the single sheet of graphite, for example. But a more precise description of 2D material is actually not only in the physical sense, is in terms of how electrons are transported along the sheet. So if you take this single sheet, electrons only have 2 dimensions to be transported. And that's why we call them 2D materials, because electrons do not have the 3rd dimension of transport, as opposed to a graphite structure, which has a 3rd dimension. But that's, I guess, more scientific definition of 2D materials.
Excellent. Great job in explaining that. I love the post-it notes. That's a really neat way of doing it. What about from the commercial side? Dave, let's start with you. When you talk about the fundamentals of graphene with people who are perhaps new to it, would you talk about it differently than perhaps we've just heard from the academic side?
Depends who I'm talking to, but yes, I'm a chemical engineer. So to me, the electronic makes perfect sense. It's a 3D orbital, the electrons are higher density electrons above and below. And I try to explain that is what gives it its functional properties. But the bigger thing that's a lot confusing out there is there's so much research, so much talk about graphene, but it's hard to characterize it, if you will. And everybody's talking about, well, mine is based on nanotubes, mine's graphene oxide. There's all kinds of graphene-like materials out there. So I guess I would just add, from a commercial standpoint, the definition is still fluid, if you will. The Graphene Council, we're a member of the Graphene Council, and they just went through a big process of trying to come up with a descriptive way to describe your product, so that number of layers, particle size, topography. So basically a categorization scheme. and they're in the process of working with ISO and other government standards to try to come up with standards to define exactly what graphene is. From our standpoint, we found that if you don't have, one or two layers, it doesn't function. You have graphite, so you don't have graphene. So you have to have a good source. We make our own, and we brought in outside auditors to actually measure, using laboratory techniques to see that you do have only, one layer, if you will, because that is critical. But yeah, so in the industry, what we know exactly what it is or what people are selling, most of the audience doesn't understand that. And you can't see the electrons, so it becomes a little bit of a challenge. You basically have to show them test data that they understand as to what the product's doing.
Interesting what you've just been sharing around the investigation into establishing some standards around different types of graphene. Industries as they emerge, it's a critical stage, establishing the standards. And certainly in my experience, suggests that we're at the point where things are going to significantly kick on from where we are now in future years. But before we move on, Emerson, from your perspective, when talking about graphene?
Yeah, I mean, from our perspective, we don't, other than David's company makes graphene, we don't produce graphene. We have a graphene library, so we buy that in, and then we functionalize using different chemistries, so we can tune it into the end use. So we're taking away the first part of it and the pain of that. We can select it from a library, but as David says, there's some very expensive graphenes and 2D nanomaterials out there. So you got to be careful commercially wise what you want. But for us, that means we've got a wealth of experience. We can dial that down, pick the chemical groups that we want to attach at which percentage, and get to the end use a lot quicker with our customer base. So yeah, we just took the pain out of trying to produce the single layers that David's talking about, which are it's a pain, but once you know what you're doing, it's quite good, David. Yeah.
Okay, listen, let's keep moving along. Thank you for that, Emerson, and thank you all. I'm going to come back to David, if that's okay, because you are manufacturing graphene, and it would be really interesting to hear from you. What are the challenges that you face in producing this product?
Well, most of those challenges came before I was with the company, if you will. But I know the biggest challenge was a reproducible product, that is consistent, high quality, and so that's a process that's under control. And then you talked about can you scale it? Is it large enough that you're not just doing it in a laboratory? It has to be something that can be commercially scaled, and then it has to be economical. So usually those things don't all work together. You can make it, but some of the processes and even the processes for making the graphene oxide, there's many different routes to make graphene oxide, and some produce high quantity, but the quality is not great. Other ones produce are low cost, but you can't get the product that you need. So we basically worked with a number of universities to develop our own and have some 30 different patents in the field. But so we kind of just figured it out ourselves, if you will, with the help of universities. But that's the challenge is consistency and being able to do it on a scalable level. Okay.
Anyone else want to come in on that one?
I can add to that if you like. David mentioned a very good point. There are a lot of claims in terms of graphene in graphene space. So then it becomes really important. What we call graphene. There are some companies that are producing graphite and calling it graphene. So it's really different grades of materials, if you will. So we have liquid phase exfoliation, for example, that gives you decent quality graphene, but the sizes of sheets could vary, for example, from maybe 500 nanometers to 1 micron. Okay, so you don't really get that single layer or high quality sheets of graphene that you get by other techniques like mechanical exfoliation, for example. And then you have graphene oxide that is a different way of reducing graphene. So it's just basically oxidizing, the basal plane of graphite, and essentially, enabling the redispersion of the graphite-based material and separating the layers. But that again has a lot of complications because you introduce a lot of functional groups like oxygen-based functional groups that results in defects, a lot of defects. And then you end up with material that is not conductive. So if you want conductivity, then you really need to have to figure out how to take it back to graphene-based system, such as reduced graphene oxide. So there are ways, again, various ways of how to transform graphene oxide to graphene-based compound, which is reduced graphene oxide, and using heat, for example, or chemical reduction methods. And some of those chemicals that are used could be quite dangerous in reduction phase. For example, hydrazine is commonly used, which is known to be carcinogenic. But there are also green alternatives, like, for example, vitamin C has been found to reduce graphene oxide and turn it into graphene-based material. I'm not talking graphene. It's just not. It's impossible, almost impossible to go from graphene oxide to completely graphene. So you will always end up with having some functional groups. So that's why the conductivity that you may get with graphene oxide is going to be a bit lower than the conductivity that you get with graphene. For example, just to give you an idea, graphite can have a conductivity up to about 1,000 Siemens per centimeter. Okay, but the conductivity of graphene that we get typically ranges from 50 to 200 Siemens per centimeter. Probably, one of the best that is out there. It's just our recent work that we achieved 150 Siemens per centimeter on graphene. Mm-hmm. And to give you just an idea, copper has a conductivity of about 600,000 Siemens per centimeter. Okay, which is way 600 times more than graphite. Okay, and then with reduced graphene oxide, on a very good day, you would get a conductivity of about like maybe 50 or 100 Siemens per centimeter. Okay.
Okay, thank you for that. We are now actually getting some questions coming in, which is always good to see in these webinars. You're never too sure if there's people out there listening. There clearly is. We've got a question on going back to what we were talking about a little earlier, when we were talking about how the electron movement is restricted to a two-dimensional plane. I mean, we're wondering whether there are any other circumstances where you might get this electron behavior with 3D materials. Is that was it you, Shayan, who was talking about the electrons?
I proposed this idea of electrons being essentially forced to go in 2 dimensions. The only if you have another layer of graphite in close proximity, graphene in close proximity, then you end up having a 3-dimensional electronic transport. But then there is a way of preventing that. So if you have, we have a range of 2D materials that are not conductive and have a thing called the band gap, wide band gap. Okay, and that means they behave similar to it's incorrect, but they are insulating materials similar to plastics. Okay, and if you have one of those in between these 2 conductive sheets, if you will, then you can prevent electronic transport in 3 dimensions. So essentially, you end up with things that are now we are calling van der Waals heterostructures and things.
Okay, thank you. I'm going to move us on to the second theme of the webinar with what's going on in today's market. and rather timely number of questions have come in on this particular topic. And someone is asking us how graphene is being used within wearable, let's go through these individually and we'll push them out there. Wearable medical textiles, so that it can be used as a telemedicine tool. Maybe Nasmul, is that something you could pick up on? Have you got some experience in that space?
Yeah, so we have been working on the wearable electronics for personalized healthcare applications. So basically, we have been looking into various kind of things using graphene. I think Cheyenne already covered some of the things in his opening speech. So what we're trying to do is we're trying to generate have a wearable which can generate and store energy, and then as well as can sense various vitals such as like temperature, heart rate, breathing rate, those kind of things. And then it can send those data to a device. So I think it is possible for medical application. This is one of the big area, but as you know, I mean, for medical, it takes years to get into market, to pass through all those regulations and other things.
Okay, thank you for that. If I could come to you, Emerson, we're also being asked about the use of graphene for heated outerwear, particularly at high altitude. And a product mentioned here, hopefully I get the pronunciation right, Siachin. Anyway, the concept, heated outerwear at high altitude, or just heated outerwear. Are you seeing this happening? Have you seen?
Yeah, extremely predominant, mainly in the East currently. There are an awful lot around Korea in that area of heated overgarments, whether they be jackets or just normal skins undergarments you would use in the sporting world. But yeah, there's a massive move towards it, because in the past everything's been run by heated wires, which are extremely inefficient and notoriously break and burn people's skin in some cases. Whereas a heated patch that we've started producing, and other people as well, we're seeing an awful lot of traction in the market. So yes, we have been asked regarding altitude, and we've also been asked regarding temperatures, because as you go up in altitude, obviously the temperature drops and the performance drops off slightly. So there is a level for obvious reasons. But yes, we have a lot of experience in it, and we are getting traction from the marketplace regarding inquiries already.
David, from your side, what are you seeing in terms of the major applications at the moment? Obviously, textile related. You're still on mute, Dave.
Sorry, our technology does not actually heat. It's more about conducting heat. So we have a hollow fiber with graphene that's made into a fiber fill. So we're seeing in a lot of jackets, but that's, so you can make a thinner, lighter jacket and keep the heat down. You can put a liner in it so that you could transporting heat. Our technology absorbs far infrared from your body. So it's taking that heat, storing that heat. And if you have a layer then that's blocking it, you get really good heat retention. So we're able to make, lighter, thinner, more effective jackets and garments, but they're not conductive. What Emerson was talking about is the next level up, which is actually, heating certain parts, using the conductivity. But
let's just open this up then, and starting with you, David, and then I'll come to the others. Just talk to us a little bit about the significant applications now that are available today in the market at retail that are using graphene.
Yeah. Okay. One of the first folks that worked with us was Contour Brands, which is Lee and Wrangler. They first put it into a jacket liner, again, to spread heat more evenly in the garment. They then put it into denim jeans. mostly in the China market where the cost was not prohibitive. And they're now working on 3 or 4 other products. So it really could be used in almost any knit or woven fabric combined with traditional fibers, cotton, wool. Our technology really doesn't do much for wicking. So you still often want to combine it with a fiber that has good moisture transport, like perhaps wool or, or a textured polyester or something. So yeah, so you could combine it anywhere. One of the shortcomings was, and this is a roll of the nylon filament. You can see it's a light gray color. The carbon is black, of course, so you get a light gray color. You can dye it, but if you're mixing it with a natural, one of the limitations was you can't really make white. So now we have a full line of products based on another 2D material, white graphene or boron nitride. So we have the same 3 polymers, nylon, polyester, and viscose in filament and staple form based on the white graphene. We call it Karim white, is keeping our same trademark, but you can make, white fabric. This is white viscose with some lycra in it. So you can make white garments as well. So color's not a problem. So now really that opens up almost any application really out there.
Yeah. Interesting that you've addressed the issue with around color. Cheyenne, products that are out there at the moment that I can go and buy.
Yeah, so before answering your question, I would like to add to David's point on color and your question around that. So now we have a wide range of 2D materials. Okay, so it's just beyond graphene. Now we've got, Dave mentioned hexagonal boron nitride, which is white, and is also insulating in terms of electrical properties, but is actually has very high thermal conductivity. So could be used for a lot of applications that require high thermal conductivity, for example. And we have a wide range of metal oxides and metal sulfides, and also things called MXene, metal carbides and nitrides. Okay, and the beauty here is by just basically changing the composition, you can also get up to electronic properties, changing color. That could be used to make, for example, strong fibers of a certain color. For example, MOS2 has this sort of, a green tinge. So if this is added to a fiber, for example, you could get some, some green color. And then you can do color matching. We are all familiar with it in textile industry that use it every day, to essentially, add some dyes and get the color that they want. But in terms of real life applications that are out there, David mentioned graphene jacket, and that's apparently taking off. But there are also other things like, graphene shoes, that graphene is used as reinforcement because, I mentioned, only 0.38% of graphene can result in a significant increase in stiffness. So that is desirable for rubber-based materials because rubbers are very soft and they can be damaged easily. And that's why in tire industry they use carbon black in order to add reinforcement to rubber. Otherwise, we wouldn't have durable tires. And that's essentially the mechanism that is used to enhance the performance of shoes by adding graphene. And it's not only that, we've got graphene bike helmet as well, and that is again the same mechanism. Here we are not really utilizing the conductivity of graphene, but is what is important for us is mechanical reinforcement. And it's surprising, during my PhD, I was a bit skeptical about the whole reinforcement of rubber, because at the time I was working on elastomeric composite, and I wanted to disprove this notion of adding graphene and getting the reinforcement. But I was surprised that I was getting the same performance with 16 weight% of carbon black that I was getting with only 0.3 weight% of graphene. So that means you just need a little bit of graphene to increase the performance in terms of the stiffness, and that could be that could lead to a reduction in the cost. That could lead to more lightweight material, and also surprisingly, when in rubber, so if you add too much fillers, you get lower tensile properties, lower stretchability. Your material fails easier. But with graphene, none of those will happen. Okay. So and also there's I want to mention this one as well. So there's, for example, graphene-based threads. There's a company, Qt Circuit, that is trying to incorporate graphene sensor-based devices in textiles. But I guess in terms of really real life, we are still at a very early stage of getting this in a real life product in a textile market.
Exactly. Thank you for that. And Emerson, your selling product, where's it being used?
Predominantly, our market volume-wise is in the East, as we would imagine. A lot of textile manufacturers over there have started incorporating it into their designs. But you do get the novel people now that are putting it into gloves and socks, whereas in the past it would be a battery and a heated wired system. Now people are putting printed patches in there with a similar battery system, but it's a lot more sustainable. It's more multi-use because you can wash it. Whereas in the past with wired systems, a lot of these products were a one-off use. So they had very high cost. Whereas now, if you've got a 30, 40 cycle washable product, all of a sudden, the price point drops for the consumer. And I think that's where we're seeing traction in the market now, because we can overcome that. It's no longer a luxury. It now becomes a mainstream product.
That's interesting. And Nasmul, what are you seeing?
Yeah, I think for the graphene application in textile, for the short term, would be graphene as an additive to improve the mechanical properties, reduce the weight, and maybe the long term, the wearable electronics is kind of more future type of applications. But we have seen a lot of resistive heater especially in the Far East market based on graphene ink, so which is slightly different from what we're talking about. The white graphene is a thermal conductivity. I mean, it's a different mechanism. I mean, you have to, I guess, hexagonal boronitride, it does like heat dissipation rather than resistive heater, which is more like using conductivity of the material to transport the heat. So, I mean, I guess we'll see a lot of application in the functional clothing area. Can we improve the performance of antibacterial, antimicrobial, even the flame resistance by some order of magnitude using graphene? But I mean, I think we haven't seen any product which is entirely made of graphene yet. And so which I believe short-term application for graphene would be as an additive to the existing product or polymer.
Okay. Well, thank you for that. Stay with me, Nasmul. I'm going to put this next question first to yourself, and we're going to move on to the topic .
Oh.
Bear with us just for 2 seconds. I had a tip off that this might happen. So just give us 2 seconds. We're just changing to another camera, I believe. If not, we'll just have to make up what that question was, Nasmul. Give us 2 seconds and they should come back. Maybe there's a couple of questions in the chat that we could have a look at. a good question here from Jonathan. Re the wicking point. If you're having sweating, how does that affect the conductivity and about the evenness as heating in terms of performance, safety, and comfort across the garment, or the impact? Does anyone have an answer for that? It's a good question. Yeah, if you're sweating, and how even is the performance going to be during that process? Nasmul, you can answer that one quickly before I've taken over.
I guess several ways you could do is, one of the way we could do is encapsulating the conductive layer so that it doesn't interact with the other thing. So yeah, I mean, the safety and comfort is definitely really important stuff. So if we are incorporating graphene into the polymer system, I guess we can overcome those kind of problem. And other impact, I'm not sure what other impact we're talking about. I guess we have seen graphene-based, washable, durable product. I'm not sure if that answered the questions.
Yeah, Jonathan's just asked, is that what is actually being done, or is that a proposal? So if you did have heating and sweating going on in the same time, obviously that safety element is massive. So yeah, is that a proposal, or is that something that that's actually being done? And then I will hand back.
I'm not sure if anyone has done on a commercial product yet, but I know people have done encapsulation on the conductive layer so that it doesn't have any impact.
Perfect.
I can add to that if that's okay. So yes, that's a way to do it, and we've done it in our strain sensor and also pressure sensor work, and that leads to so we got I think 50 cycles of washing at 80 degrees Celsius without a change in conductivity. So that essentially indicates that you get some sweat resistance. Of course, you have additional stuff in sweat than just basically standard washing. But that we haven't really looked into sweat resistance. But our initial investigation showed that we can wash our graphene-based fibers, at high temperature, 80 degrees Celsius, for over 50 cycles without significant change in contact.
Thank you, Sharon.
We're back. Thank you. Hopefully you can hear me, and thank you for stepping in there, Becky. Much appreciated. I was trying to move us on when we were rudely interrupted to the topic of sustainability. And I was going to ask a very general question, is graphene sustainable? But we've actually had something a little bit more specific come through from the audience. And the question is, how sustainable is white graphene compared to bleach if you were to use it as a dye pigment in textile applications? I'll maybe start with Emerson on this one. This sounds like it's right up your street.
No, I disagree. It's not up my street, that one. I'm sure there's somebody better placed to answer that one. I'm not the chemical engineer on the panel.
Well, we've got two chemical engineers from memory. Let's go to Dave.
Yeah, that's a good question. And you have to kind of back up a step, if you ask me, because, sustainability, what does it mean to you? And I'm working with a lot of brands, and some brands, sustainability means that your chemical process of producing the fiber and the clothing and the dyeing is all done with the lowest amount of energy or wastewater or whatever. Some have gotten very simple and just said, we're going to use recycled materials. For us, sustainability is recycled. And by 2025, we're going to have 50% or 100% of our clothing will be made with recycled. I mean, so the definition of what is sustainable depends on the actual customer and what they're going. I mean, the industry in itself has struggled with this, and there's been a lot of seminars, a lot of discussion. So sustainability means a lot of different things. How much energy is being produced, how much chemicals being produced. And traditionally, with inks and dyeing and clothing, there were a lot of chemicals, a lot of energy, used to produce a fabric or a garment. Some people are going the complete a way around, and I think Levi's is one that's starting in the public to to push this a bit, is, you know, in our culture today, especially in the US, you know, you buy something, you want it cheap, and you keep it for a year and you throw it out. Now, how is that sustainable, right? I mean, because could you recycle it? Maybe, but most of our clothes are made of 5 different polymers. You know, they're cotton, they're wool, they're lycra, and they're polyester, and something else thrown in. So you got 4 or 5 fibers. So recycling clothing is talked about, but you know, unlike PET pop bottles that are all made of the same polymer, and you can easily melt them and recycle them into recycled polyester, which we have recycled polyester that we can put graphene in, and we are doing that today. We have a product on the market you can buy. So if people want recycled, you can go that way. But I think this question was about bleach. And again, can you eliminate like the bleaching part? Well, it is very, very white. So perhaps yes. I mean, I don't think you would need to bleach it. Like cotton, you still have to bleach to get it to be white. So it could be a good alternative there because it starts with a very white pigment. So yeah, the sustainability is a big question in itself. And I think from our standpoint, what I try to talk to people about is our pigment, our graphene in our white is in the fiber. It's in a very small percentage, but it will last as long as you have the clothing. I mean, not 5, 10, 20, 30 washes. It'll last for 20 years because it's not going anywhere. It's in the polymer itself. So as long as there's still some fabric left on your shirt, it's gonna continue to function. So and to me, that's sustainable because you're not buying 5 or 6 more garments. You can wear it longer. It actually wouldn't need to be washed as long if it has anti-odor, right, and antibacterial. It essentially can stay clean longer. And it's the washing that uses a lot of energy and creates a lot of waste and actually degrades your fabric, right? The more times you wash it, is the less life of your garment. So I think you get a longer life garment that's functional all the time. So to me, that's a pretty good goal towards sustainability. That also becomes a little harder to get into the consumer's mind when they're out there buying it. So that's kind of my long answer to a short question.
Yeah, and I think that of course there's so many factors impacting on this very, very broad topic of sustainability, from consumers and how they behave through to government policy. But I would like to perhaps just let's move away from white graphene and just talk more generally. Nasmul, is graphene sustainable, however way you want to define it?
That's very, very good questions. I mean, I think I agree with Dave. He has made really good point about the sustainability, what it actually means to individual people. I mean, you have to look at the environmental impact, social impact, economical impact of the whole thing. Then we come up with some number or some data. Without the data, it's really difficult to say whether this process is sustainable or not. I guess with the graphene, I would say how you manufacture graphene is quite important. I mean, whether in the process, are you using any toxic chemicals? What kind of byproduct we are discharging to the environment? These are quite important. I've not seen any data-driven studies so far which would back up that the graphene, or I mean, it's really difficult to say. I mean, but what we have been focusing is mainly on water-based formulation, which is non-toxic and good for textile applications. So in that way, which is, I believe, a little bit more, but without data, I think it's really difficult to say whether it's environmentally sustainable over the existing process or not. So
fair comment. Cheyenne, have you anything to add on that?
No, I think David and Nasmul put it really perfectly, in my opinion. So without complete life cycle analysis, it's really hard to say But if sustainability means durability, for example, because you buy less product, you prevent fast fashion and things like that, then obviously this is going to be helpful. But in terms of manufacturing, we have a lot of materials that are not really produced in a sustainable way, like Teflon, for example. We've all heard stories about that, how the byproduct of the synthesis was discharged in rivers and polluted the environment. So luckily, we are not really dealing with any, material that is very dangerous to the environment during the synthesis or processing graphene or graphene-based materials. Nasmul mentioned, mostly we deal with water-based solutions, which are, safe to deal with, and also graphene is very stable, so it doesn't really react with other materials in the environment as much. So you get a lot of properties that are favorable towards sustainability. I would put it this way.
Thank you for that, Emerson.
I think I concur with the other three guys. I think we've touched on everything, and I'm more at the front end maybe with customers similar to Dave and what they're after, and life cycle is a big thing of that, and shelf life. So like we said, washability, durability of the products. We don't produce graphene, so that's not really my thing as such. We use graphenes, sure. But our products that we're producing, for instance, to take it into another technology, we use airings in RFID. So, we're being asked by RFID companies, can they recycle it? Yeah. So okay. in that field, we're looking into it, and it's an ongoing study. You can't just get to that point overnight.
Absolutely, none of this is gonna get resolved overnight. That's for sure. Thank you. We've got a lot of questions coming in now, and one just related to sustainability, and I think we've answered it, but let me check. It says here, I'm unsure if performance after several wash and dry cycles would represent the same underlying behavior. Now, I think what we've been saying is that graphene does improve the longevity of product. Is that correct? Is that what I've been hearing from you panelists?
I would like to pick that one. So I think that referred to my argument in terms of washability of graphene-based material, and how conductivity remains stable, for example. That does indicate, that gives us an indication at least. So the material on the stability of the conductivity of the material during washing and during wear as well. So I don't expect, for example, sweat to be an issue during the sensing performance, because what is important during sensing, for example, is just basically changes in conductivity rather than the effect of, for example, sweat. I think we have an idea about the durability of the material. But then the real life performance could vary. But I think this tells us that if we have like graphene based, for example, sensor or graphene based material embedded into fibers, we can get conductivity that is stable for a period of time during washing, during wear.
That to Shayaz, but I completely agree with Shayaz on that point. We also have done. We haven't done anything on the sweat, but we have done durability to wash test using a standard AATCC or British standard, like up to 10, 20 or 30 cycles. It's been really, really stable. The conductivity hasn't changed much. So it has been reported in the paper. So publication is out there. If people are interested, they can read it.
Like I say, lots of questions coming in now, so I'm going to do my very best with your help to get through them. Something very specific here. Can graphene be screen printed?
Okay, so I'll take that one. So yeah, 95% of the inks I sell are screen printable. Yeah, we manufacture flatbed screen printable inks, but they can also be turned into rotary screen. So yes is the answer. Absolutely no problem. How much do you want?
There speaks a good salesman. How much do you want? Do you also manufacture graphene inks with graphene in for inkjet printing?
We are looking into it. The printer head of inkjet printing is the issue at the end of the day there. So yes, it's on the radar. Yes, we've spoken to people, but the actual technology itself is the issue, not putting graphene into it. Yeah. Got it.
This is definitely already the question of the day. The next question: does any kind of graphene have stealth properties, as in a stealth aeroplane? So, I guess we're imagining here that we could wear a graphene-based suit and just completely disappear in front of people. Anyway. Told you it was the question of the day. Anyone want to pick up on that one? No. Okay.
I've got some comment on that though. I'm not aware of graphene-based material that can do that, but carbon nanotube sheets under application of current have some certain stealth behavior.
Okay.
We've got something out of carbon-based materials, and I can't discuss much about the mechanism here because that will be very complex and out of focus of this webinar today.
Terrific. Well, I'm so glad we got an answer to that question. That's really interesting. Another question come in. When it comes to the end of life of a textile and the fiber has been already, it's a fiber graphene composite, for want of a better word. Is it possible to then separate out the raw material for the fiber and the graphene? Is that something that's been looked at? If the answer is no, that's fine. We can move on.
Yes, I'm aware. I mean, I've not seen anything like that yet, but I mean, I guess it depends on how it has been applied on the fabric. So if it is become part of the fiber, obviously it's a carbon. So how it's fixed with the fiber, that it lot depends on how it's been applied on textiles, whether it's been functionalized or coated on the fabric. So yeah, I mean, I've not seen anything.
I guess I would just make a comment. You know, if you look at textiles, you know, you've gotten almost all the things that we're wearing. Well, some of them are 100% one thing, 100% polyester, 100% cotton, but most are mixed, and that becomes the biggest issue if you're trying to recycle. You know, we're putting in graphene oxide at like 1 or 2%. So it's a very small particle, very fine particle that's in the fiber. So yeah, you're not going to really be able to separate it at end of life, but it's as like a pigment, it could go along for the ride. So if you were recycling the polyester, it would go along and it wouldn't melt, but it would go along with the stream, and you could still reprocess it into a usable product. But right now, if you look at fabrics, very little are being really reprocessed because you need the infrastructure. You have to collect it, separate it, and then put it back into some usable product. So there are people working on that, and it's being done on small scale where people are taking fishing nets and some things and recycle them back into a product. But the infrastructure of gathering them, separating them, and like I say, in textiles is extremely going to be a big challenge because there's so many materials combined into the same stream.
It is a perennial problem, and one that I think is being addressed in one of the Scandinavian countries, and certainly the new European strategy for textiles has that at its heart, the circularity of the product, but the perennial challenge of mixed fibers in one fabric. Moving on, another question, Cheyenne, this one's for you. someone who's very impressed with your research work is asking could you please tell us a little bit more about the benefits of liquid graphene, and could it be mixed with nano silver as a printing paste for making electrodes? A couple of questions there for you.
Okay, so is it liquid crystal-based graphene? I think that they're talking about. So liquid crystal-based graphene are, a bit, I guess, like different in a way that they kind of form domains, and these domains could be used for reinforcement. Okay, so if you increase the concentration, you get a paste-like material that could be processed in whichever way you like. We can extrusion print this material, we can 3D print it. The concentration will be, so for example, at about 10 to 15 milligrams per milliliter, it would be like a honey-like paste that then you can take and, for example, print it. Another application or another property of liquid crystal-based material is liquid crystals are domains, as I mentioned, and they can host a lot of other additives. So you can essentially, they can accommodate other particles and fillers and polymers and things like that. In my studies showed that actually had up to 90% of other additives added to a liquid crystal graphene oxide, and it still maintained its liquid crystal behavior. So that means that if that is the case for the person who asked this question, yes, we can definitely add additives, but we need to be careful about this, the chemistry of the system as well. So these are negatively charged sheets and if you are trying to add positively charged species to this material, then there will be aggregation. So I guess we need to really look into the chemistry and make sure that we enable the interactions of the phases so that we have a stable formulation.
Excellent, thank you. Nasmul, a question for you here. Does graphene or HBN biodegrade? And if it does, what would be the impact on either the soil or water?
To be honest, I haven't done such a study yet, so I don't know the answer.
Has anyone here in the panel studied this at all? No. Okay, good question. You floored the panelists. It is a good. No?
I just add that we've done biomedical studies, like we grew cells on top of these materials. They are biocompatible. I can comment on biocompatibility, but I don't know about the degradability of these materials, to be honest. Other things such as, for example, I've worked with titanium carbide, and you can actually degrade, they can be degraded to things such as titanium oxide, if that helps. So you really need to look into chemistry. Things like hexagonal boron nitride and graphene, they're stable. They don't degrade easily. But things like, transition metal carbide, then depending on the chemistry, you can, for example, cook them and they turn into TiO2 and carbon. Okay, so.
Good. Well, thank you for that. Straightforward question: is graphene Ecotech certified? No one?
Yeah, we have Ecotech certification on our product. Yes.
Okay. So it's to put not so much the fundamental graphene product, but the product that you're producing from it that would be Ecotech certified.
Karim fiber, yes. Mm-hmm.
Cool. Okay, thank you. So just before we reach a conclusion, because we are now up against the clock, just a couple of minutes left, I'd like to give each of you perhaps, say 1 minute, just to tell us about where you think the market for graphene and other 2D materials might go in the next, say, 5, maybe even up to 10 years. I think this will be very interesting. And Nasmul, I am going to come to you first with that one. Give us your view. What's your vision for graphene in textiles, of course?
Yeah, thanks. Sorry, I'm probably not repeating myself. I mean, the short term, what we would see is the application in the high performance clothing, and the long term is the wearable electronics. But also, just to add to that one, obviously sustainability will be really key things. How we can incorporate graphene into recycled material to improve their performance, to make it reusable, and can we increase the recyclability of the product as well by adding a small amount of graphene and other two-dimensional material. I believe that this is a really exciting field of research. As Shayan mentioned, graphene, not only graphene, there are like hundreds of other two-dimensional material we could explore, and we can do like a mix and matching, not only to make for the color, but for various applications. So I think the future would be more kind of like a tailored material, designer material. Can we mix different kind of two-dimensional material, come up with a product which can serve a specific purpose? So, and in terms of the commercialization, I guess it would be good to look at specific application-driven product. So graphene is not, I mean, there is no universal graphene, I would say. I mean, we have to customize for specific applications and specific functionalities. So these are kind of like few things.
Thank you. Thank you very much. Emerson, the future, where are we going?
So from our side, we've seen a massive uplift in boron nitride, similar to what David's been talking about earlier, for various applications. But we have many things on the horizon. Scale-up's been a big part of our business, but you know, moving in towards lithium-ion batteries, I know it's not quite textiles, and semiconductors is a big growth industry using graphenes, and I know Shayan has already alluded to that earlier on. So you know, the wearable technology is going to become more prominent as everybody understands what it does and what it can do, and I think we're ahead of the curve currently. So for us, yeah, the future is very bright.
That's great to hear. And Shayan.
Yeah, I guess Nasmul and Emerson, they wrapped it up pretty well, to be honest. You know, it's a very exciting time. We've got a range of new materials that we haven't had before. So we've got, you know, graphene, we've got, you know, hexagonal boron nitride, we've got, you know, metal oxides, and we've got maxines that can give us the performance depending on the application that we want. Really, you know, Emerson initially earlier on today mentioned about EMR shielding. I think that is going to take off as well, and also, you know, eventually we get to a point that we really use textile-based wearable devices rather than, you know, having, for example, smart watches. You know, our textiles, our clothes could do the same things as for example, our smart watches. We are nearly there. So we have, you know, strain sensor textiles based on graphene. We have pressure sensors. We have touch sensors. We have also, you know, supercapacitors that can store energy. It's just basically, you know, how we combine these together and make, you know, flexible and wearable textiles that can give us a wide range of functionality.
Terrific, terrific. And David, you have the final word.
Well, short term for us, it's more products. We're working on flame retardant grades. We have a grade that we just launched on that does have wicking. So for us, it's to have a broader range of textiles that can be immediately used in fabrics that we wear. But I think if you look at the research going on, the wearables is next. My guess is it will start in, niche applications, medical space, the things that can really afford expensive technology and have development, have real need for it, and eventually get to the general use. I mean, I went for a treadmill test the other day and they strap 20 electrodes on you, and then you're supposed to walk on a treadmill. I mean, I can see a day in the not that distant future where you put a t-shirt on and it's already built in and can measure all that heart rate, oxygen sensors, and probably come one at a time, right? Focus on heart rate, or maybe a different shirt for oxygen because you have different mechanisms. But I could see where in the future wearable smart textiles will become more and more, more common, probably starting in the medical field.
Yes, I hear this a lot, and I'm sure, I hope you passed that test that you had to go through yesterday satisfactorily. So we're now up against it. The credits are rolling. I would like just to begin by saying, or end by saying, that my thanks to all of our panelists today. A huge amount of knowledge in the panel, which I know has been incredibly well received by the audience, because I've been watching all the comments as well as the questions coming in. They all want to make contact with you. I'm sure we can share details for that. And I would say to the audience, I connected with these guys myself on LinkedIn over the last couple of days, so you can find them all there. On LinkedIn. And in answer to one final question, yes, this session has been recorded and it will be available on the Textile Institute YouTube channel, and I'm sure we'll be sharing a link with you in the very near future. So that's it. We're done. Thank you again, gentlemen. Hope you, our delegates, enjoyed today's session, and we all hope to see you again sometime very soon. Thank you very much. Bye, everyone.
Thank you very much.